Yesterday? Nice.
There was, there was like, no, they weren't. There was like the back of my seat. Like,
Oh,
there's
yeah.
like a crack between the seats. I checked there, but there's like a second crack.
Oh, yeah.
Like, there's like a hinge where the
Uh-huh.
seat goes into the car, and then there's like a
Oh, man.
second crack. I guess it must have slipped there when I threw my sunglasses, but I'm so mad. Only ended up being 5 minutes late for work, though. So.
That's not so bad.
Yeah.
Okay, so tomorrow's exam 2. Hi, that's right. So the topics for exam 2 are rigid body, free body diagrams, rigid body statics, and centroids. And we'll finish talking about centroids today and then move on to the next thing. And remember, one of the questions on here will be derive the magnitude, or the formula for the moment produced by a couple, and give an example of how that works. So, come up with sort of an example problem and show how that formula works. I would want to make sure that you can use that formula that you derive. But I will not tell you which number. So it could be number 1, it could be number 3. Okay. Yeah. So you have to be flexible with that. One thing you could do is you could just do that one first, and so whatever number it is, you could act like it's number 1. Just do it first. That will be on the actual exam. So that's free points. I'm not free though, because you got to do it. When I taught Intro to Engineering, I always did this thing. You guys who took Intro to Engineering, it's like, you work with transistors and all this stuff. And so, but not everybody does the same things on the project. So I wanted to make sure people knew how to do like some important things. And so one of the problems was I like drew the devices and then had people just draw the wires. Did I do that in your class yet? Maybe I hadn't done that yet, but so just connect the wires that makes this transistor work, And so before the test, I said okay, here's a handout of what's actually going to be the question on the test. And in case you can't figure it out for yourself, here's where you have to draw wires to make it so the transistor works, And this is going to be on the final, and I went through it a couple times and gave people the handouts and put it on D2L and everything. And then the test came and 2/3 of the people in the class just basically put random stuff down, well, this is just right out of left field. So don't be like those guys. I just always, every time I graded those, I just dreaded it, People would connect wires from every point to every other point. There'd be 600 wires, Okay. There was one, you guys, I think yesterday asked if I would do an example in class. Is that right? Can you remind me what that was? It was the one that looks like a chair. So the practice problem, which number is it? Okay. And so you have this funny shaped object like this, and it's connected to a pin like here. Is that right?
And then your origin's like right above that left.
Over here. Does anyone have it? The sheet? And you just wanted to see
If you put the
if
point at the origin,
yeah.
from you end up with a full system of equations.
Okay.
Just wanted to see how you set up.
Oh yeah, okay.
Oh yeah, you need that like row echelon.
So yeah. Well, let me save this one then, because we're going to get to that today, and I'll give a little more detail about how to set that up. And I'll use this example when we get to it. Yeah. Okay, so last time I talked about how to calculate the centroid. You can do it as an integral. Hopefully you don't have to. Hopefully it's a shape that there's already a formula for. In that case, using the formula is just about sort of in your mind flipping the shape around to whatever orientation it's in, and then coming up with coordinates based on what your origin is, what your coordinate system is. And then you can also combine a bunch of those shapes. If you have a complicated shape that's like a combination of rectangles and triangles or whatever, circles, you can use the sum formula. So now all we have to do, I mean, that's really all there is to the centroid problems, but you have to know how to connect those to actual, statics problems. So here are the two ways that those come up in statics problems. There are two uses for centroid calculations. The first one is finding the center of mass of an object. And the second one is let me write that as expressing a distributed load as a point force. And notice that both of these, they're kind of the same idea, and in fact, oftentimes distributed loads come from the weight of an object. So what both of these are doing is finding an equipolant system where a distributed load is represented as a point force. Obviously, that's what we're doing with distributed loads, but that's also what we're doing when we represent the weight of an object that's pulling on, the weight's actually pulling on every point on the object, and we choose a point to where we're going to apply just a single force. Okay, so first, let's talk about finding the center of mass. As long as an object is homogeneous, and homogeneous means that it's the same material everywhere. So the same material properties at every location. The center of mass is at the centroid. If the material isn't homogeneous, then the center of mass is really, so you find the center of mass using the formula, the total mass times the center of mass is equal to the integral over the area of the mass of the increment of area times the centroid of that increment of area times, so how do I want to say this? Sorry, change this. So change this to an integral over the whole mass, and you're going to integrate the center of mass of each element times an increment of mass. And so the idea is just, instead of using area or volume, you just have to use mass. All the ways of breaking it up still work, so you can still do it as a sum. So the sum formula still works. So the total mass times the centroid, or times the center of mass, is equal to the sum for I equals 1 to n of the individual mass times the center of mass of the individual piece. Okay. And if you're doing it in 3D, you can do it with 3 components the same way. If the material's homogeneous, then, like, notice that what this is really is a weighted average. When you use that sum formula, you're figuring out how much, so you break up a big object into pieces, and you figure out how much the centroid of one piece affects the entire centroid based on how much area it has or how much volume it has. You know, that's how many votes it gets in the average. And if you have a homogeneous material, area or volume, they're both stand-ins for mass. The ratios are the same. You know, the ratio of the area of the piece to the whole is the same as the ratio of the mass of the piece to the mass of the whole. So that's why it's the same thing. We're only going to deal with homogeneous materials, but if you had an object that part of it was wood and part of it was steel, you'd have to use the mass formula instead. But inside the individual pieces, you could still use the area formula. Any questions about that? All right, so now for distributed loads, we're going to see a lot of problems where, like, for example, you have a beam and the load acting on the beam is represented with something like this, where you're given like a function for the values of the distributed load in terms of newtons per meter. So this point up here would be something like, 10,000 newtons per meter. And basically what it means, and if you know that the length here is, let's say this is 2 meters, okay, then this is a function that lets you figure out what the distributed load is at any point, okay? And what that means is, so let's go halfway. At this point, what would be the value of the distributed load there? Halfway between 0 and 10,000. Good, 5,000. So what that means is there's not a point force of 5,000 newtons acting there. In fact, what's the magnitude of the point force there? It's 0. I mean, if you have a distributed load, you don't get any finite force unless you have some amount of area that it's spread out over, okay? But the value of that distributed load says if the whole thing had this distributed load of 5,000, well, let's say if an entire meter had a distributed load of 5,000, then you'd have a total force of 5,000 newtons, okay? So that's what that means. And so if every meter with a value of 5,000 newtons per meter has a total force on it of 5,000 newtons. And what we want to do is we want to take this distributed load and represent it as a point force, okay? And the way to do that is just think of the shape of that distributed load and calculate the centroid of it. That's where it acts, okay? Where it acts matters for the behavior of it, right? Like if the entire force acted out at this end, it would require a bigger couple at the wall to keep it from rotating than if the entire force acted at the wall, okay? So you use the centroid to find the location of that point force. What about the magnitude of the point force? How do you find that? Well, that's the area, okay? So the area of the distributed load shape is the magnitude of the point force and the centroid of the distributed load shape is the point where that force acts. Okay, so let me do this problem as an example. For the figure above, bless you. What are the reaction loads at the wall? I'm going to neglect the weight, so we only have to deal with this distributed load. All right, so the distributed load shape is a triangle, and it's not drawn to scale, because if I drew it to scale, it would look really crazy. It would have a width of 2 and a height of 10,000. But it's a triangle with a base of 2. That's in meters. And a height of 10,000. That's in newtons per meter. The area is 2 times 10,000 divided by 2. So 10,000. And notice that the units come out the way that you want them to. Base times height over 2 gives you newtons over meters times meters, so you just end up with newtons. And the centroid is a third of the way, bless you, it's a third of the way this way, and a third of the way this way. So the centroid is going to be right here. Okay. What's a third of 2 meters? Yep. So 0.667 meters. And what's a third of 10,000 newtons per meter? Yeah. So 3 newtons per meter. Only one of these two matters to us. Can you tell which one that is? And why would it be? The 0.667 matters. The 3333 doesn't matter because all of these, this distributed load is pointed down, right? And so this point force is acting straight down. And you can move a point force anywhere along its line of action without changing its behavior. And so we end up with a downward point force like that. We can locate it up or down anywhere. It doesn't change the problem. So the only thing that matters is that we have the horizontal position right. Okay. So you can skip the part for these weight or these downward distributed loads. You can skip the part about calculating the vertical location of that centroid. Okay. All you need is the horizontal location of the centroid. So 0.667 meters from the right side. Okay, so let's draw a free body diagram. Now I'm going to replace that distributed load with a point force of 10,000. And the distance from here to here is 0.667 meters. What are the loads produced by the fixed joint at the wall? Yep, so there's a couple, and then there's a unknown force vector. So now to fill out the table, we have to choose a coordinate system. I guess I'll choose the origin here, and I'll also choose that to be the about point. So fill out the table: pancake, artists, row 4, marzipan. So first I'll do the loads at the wall. We're calling that the origin. The about point is also the origin. So the row vector is 0. The force vector is RAX, RAY. And so the moment produced by that force vector is 0. And then we have the couple, and we don't care about any of these other values. and now the 10,000 Newton force. If the coordinate system is at the wall, what are the coordinates where this point is acting? Yep, that's right. So the x component is negative 0.667, and then the y component, we don't care what that is, I'll just call that 0. The about point is the origin. The row vector is negative 0.667, 0. The force vector is 0, negative 10,000. And so the answer is 6,667 Newton meters. And so now put it into Newton's laws. Newton's second law says Ra plus 0, negative 10,000 is equal to 0. And you can just solve that right off the bat. So the force vector Ra is equal to 0, positive 10,000 newtons. And the rotational equation says Mr plus 6667 is equal to 0. So Mr is equal to negative 6667 Newton meters. Any questions about that? So you're calculating the area of the shape and the centroid of the shape. Well, even just one component of the centroid. This is kind of, I want to just say one more thing about this. This is sort of for future reference because it doesn't really matter to us yet. But when we start talking about internal loads, so when I mentioned at the start of the class that the idea of internal loads is that if you take a stick like this and apply forces to bend it, the fracture isn't going to happen where you apply the forces. So there must be something else going on to cause that fracture. And to get at that, we're going to talk about internal loads. And when we're talking about internal loads, there's a right time and a wrong time to treat the distributed loads as point forces, okay? And that includes the weight of the object. So the weight is a distributed load. It's just it's like a rectangular distributed load, a uniform distributed load. For now, I mean, everything that we're doing, you can just treat it as a point force right away. But when we start talking about internal loads, you have to wait until you've chosen a part of the body to isolate. And so that's sort of the general answer to, like, when can you treat a distributed load as a point force? Once you have chosen what to isolate, drawn the free body, then you can replace a distributed load with a point force. Okay, so notice don't replace a distributed load with a point force until you've chosen a free body to isolate. Okay. So that's the end of the stuff that's relevant for the test tomorrow. If anyone has any questions about practice problems that relate to the test, I'd be happy to answer those. Except that one is going to make sense in just a second, so let me do that after we move on a little more. But anybody have any questions about practice problems you'd like to see?
The last one,
Okay, do you have, can I see that again?
Your numbers kind of funny, or maybe mine not.
Okay. Number 5. All right. So this is on rigid body statics. So rigid body statics, number 5. This is the one that looks like, so you have one side connected by a pin joint to the wall. And the other side connected by a pin and slot joint. And let me draw this again just to make it clear that these angles are different. So we have the body like that. And then that pin slides in a slot like this. The mass is 850 kilograms. This angle is 45 degrees. But that's not the same as this angle. This angle is 20 degrees from vertical. So this angle is 20 degrees.
What wouldn't that be? Oh, okay. It's vertical down.
Either way,
Oh, yeah.
because of SAT math. So that angle is equal to that one. You guys are going to be so ready for the SATs after this. All right, so we're going to isolate the bar. There's a downward force. What's 850 times 9.81? Okay. And up here, this is a pin joint. So this is the easy one. I'll do that one first to build up some momentum. And then down here, this is a pin and slot. So we know that the force is going to be perpendicular to the slot, right? So drawing it isn't too bad. Which direction? So perpendicular to the slot, there's 2 possible directions. Which one do I want to use? Well, it doesn't matter. You can choose either one of those and you'll get the same answer. You'll get, one way you'll get a positive number, one way you'll get a negative number. But if you plug that back in to calculate the force vector, in either case, you'd get the same thing. So it doesn't matter. So I guess I'll draw it, well, I'll draw it out just to make it less cluttered. So I'll call this RA. And is there any reason to choose one about point over another one in this problem? There's one minor reason, it doesn't really matter, but we have 2 unknown forces here and only 1 unknown force here, so I would put the about point up here at B. And so let's figure out how we're going to represent this force using a unit vector. So, oh, yes. 4 meters. Okay, so if we're going to use cosine and sine to come up with a unit vector in this direction, what's the angle that I want to use with that? Well, the way to do it is start with your vector in the positive x direction, and then we want to rotate it until it is, well, we want to rotate it so it's in this direction. The way that occurs to me to do it is, so I'm first going to rotate it positive 90, so it's like that. Then another 20, so it's like that. So now we're up to 110. And now we want something perpendicular to that. So 90 plus 110 is 200 degrees. Okay. Any questions about that? If you drew it the other way, then it's just going to be positive 20. You're going to go like the way I would do it, because I'm simple-minded, is I would go from here 90 degrees to there, another 20 degrees to there, and then subtract 90, so you end up with 20. Okay, so write the table. Pancake artists, row 4, marzipan. Yeah, let's do that. Okay, so I'll start out at the origin. RB is acting at the point 0, 0. The about point is 0, 0. So the row vector is 0. The force vector is RB, x and y. And so the moment is 0. Now I guess I'll do the point A, because then I know this one's just the midpoint between those two. I can just average those two. So what is 4 times 0.7071? Negative 2.83. Okay, so the point A in this coordinate system is negative 2.83, negative 2.83. The about point is 0. So the row vector is negative 2.83, negative 2.83. And so the force vector, well, I guess we never calculated that, but it's going to be RA times the cosine of 200, RA times the sine of 200. Can someone calculate that cross product? You can leave out the RAs because everything's going to have an RA multiplied to it. So what's negative 2.83, negative 2.83 crossed with whatever cosine and sine of 200 is? What is it? Okay, negative 1.69 RA. And so then where the weight force is acting, that's going to be at the average of, it's at the midpoint between these two. So it's going to be the average of 0 and negative 2.83. Negative 2.83. So negative 1.41, negative 1.41. About point is 0. So the row vector is negative 1.41, negative 1.41. The weight force is 0, negative 8338.5. And what's negative 1.41 times negative 8338? 1179. Okay. Okay. Yep. Just the location. Well, I just mentioned this yesterday, I think. If you ever want to find the midpoint between 2 points that you know the coordinates of, you can just average the 2 sets of coordinates. So I just average 0 in these, which is just half of this. Okay, so Newton's second law says RBX, RBY plus, what's cosine and sine of 200? I'll just, oh yeah, 200. So yeah, 940, and then this one is negative 0.342 RA. Plus 0, negative 8338.5 is equal to zeros. And the rotational equation says negative 1.69 RA plus 11,792.4 is equal to 0. And so then, you know, you can solve for RA here, plug it in to this one, and it gives you RB. Any questions about that one? Any other questions about practice problems for the test? Okay. So the next thing we're getting into is structures. And the idea of structures is just collections of rigid bodies, you know, connected by joints. And I think, to me, this is sort of the heart of this class. This is the one thing, like coming out of statics, this is what people really expect you to have covered well, know how to do well. So this is, any structure is a collection of rigid bodies connected by joints. We deal with this kind of stuff in dynamics too. So if it's stable in equilibrium, so if it stays still, it's a structure. So that's what we're talking about now. If a collection of rigid bodies moves, it's called a linkage. And so we'll talk about linkages in the next class in dynamics. Oh, by the way, I posted, if you look on the dynamics D2L page for the people who are taking dynamics, I posted all the old lecture videos and notes, so you can look through those and start to, you know, figure out if you want to drop or not. Okay, and structures is really where doing systems, big systems of equations for big numbers of variables is going to become an issue. So this topic is really kind of about the cosmic struggle between the good guys the equations, and the bad guys the variables. And so there's just going to be a lot of bookkeeping, like, okay, how many variables do I have now? Do I have enough equations to solve it? At each step, I'm going to, suggest, like when I go through a method for structures, at each step, you're going to count up the variables you have, count up the equations you have. If you don't have enough equations, you have to move on. Sometimes moving on introduces new variables. It's kind of a big bookkeeping thing. But you're usually going to end up with at least, so on exams, I'll probably do problems where you have 6 variables and 6 equations. But those are like the small problems. For problem sets, you'll have things where you have 18 variables and 18 equations. And obviously, you don't want to do those by hand. So, I mean, maybe you do. Yeah, right. So you'll have systems of equations as big as, let's say, 20 by 20. So you'll need to do that on a computer or on your calculator. And so I mentioned this method once before, but I just want to give a little more detail on it. The easiest way to do it is reduced row echelon form. It's a catchy name. And in your calculators, at least in TI calculators and in MATLAB also, and in most things, this is abbreviated as RREF. So RREF is always something that you can use to solve big systems of equations. So let's say, for example, you have the system 4u minus 3a minus 20 equals 0. And then a minus 15 is equal to 2u. And then a plus b minus 5 is equal to 5. And you want to solve that system. So the first thing you have to do is figure out if it's possible to solve. This has 3 variables, a, b, and u, and 3 equations. So as long as none of these equations are linear multiples of each other, we can solve this. You don't know that for sure. I mean, because with a big system of equations, it's pretty much not possible to eyeball it and know whether you have any linear combinations. But these have to be independent equations. So the steps that you want to follow are first, so here's the approach. Choose an order for the variables. Doesn't matter what the order is. For this one, I'll choose, what did I do? A, B, U, I think. So first is A, second is B, and third is U. But you could choose any order, you just have to keep it consistent. And once you've chosen that order, write your equations, I guess rewrite your equations. with your variables in that order, in your chosen order. And this is important, and it's easy to forget, all your constants on the right side of the equation. Or all your constants on the opposite side of the equation. So if I rewrite those ones I just gave you, they are negative 3a plus 0b plus 4u is equal to positive 20. The second equation is 1a plus 0b minus 2u is equal to 15. And the third one, 1a plus 1b plus 0u is equal to positive 10. Then once you have it in this order, the next step is to write what's called the augmented matrix. And the augmented matrix is just however many rows as you have equations, and one more than the number of variables columns. Okay, the number of columns is one more than the number of variables you have. So in this case, we're going to have 3 rows and 4 columns. This first row represents equation 1. The second one represents equation 2. The third one represents equation 3. And the rows represent the variables. So this represents the columns represent the variables. So this is A, B, U, and then this is the constants. And now I'm just going to go through and write all these coefficients. So negative 3, 0, 4, positive 20. And then 1, 0, negative 2, 15. And then 1, 1, 0, 10. By the way, if you have a TI-89 titanium, there's a simultaneous equation solver that isn't really any easier than reduced row echelon form. It does make it a little easier to read the answers when you get done. But you use this the same order of entering your variables for the simultaneous equation solver that you do for the augmented matrix for reduced row echelon form. Okay, so that's the matrix. And in a TI calculator, there are 2 ways to do it. The first way is square brackets, commas separating values that are on the same row, and semicolons separating the rows. So negative 3, comma 0, comma 4, comma 20, and now semicolon, 1, comma 0, comma negative 2, comma 15, semicolon, 1, comma 1, comma 0, comma 10, and then close the square bracket. And the other way to do it is, instead of semicolons denoting the ends of the rows are enclosed in square brackets of their own. So you can also do this as square bracket, and then square bracket to start the first row. So negative 3, 0, 4, 20, end first row, start second row, 1, 0, -2, 15, end second row, start third row, 1, 1, 0, 10, end third, end matrix. And I think there are some calculators that don't have a semicolon, or at least I couldn't find it when I was looking at it. So some of you might have to use this one. All right, so now, and either way, use the store function. Looks like an arrow. Put it in some variable name, A or M or whatever. And then to use the reduced row echelon form, go to catalog, RREF as the argument, put in your matrix that you just defined, M. And what it'll give you is a matrix with a lot of useless information. 1, 0, 0, 0, 1, 0, 0, 0, 1. So that part doesn't tell you anything. But the last column of the matrix that it gives you will be the answers in the order that you chose. So you'll get -50 if you enter in this matrix, +60, -32.5. And that means that A is equal to -50, B is equal to +60, and U is equal to -32.5. Any questions about that right now? Yep. Yeah, you can. Yep, you can do that. And you can also, I think, at least most of you can go to, like, there's a math button or something on there. And if you go into math and then go into the matrix functions, RREF is one of the matrix functions. So you don't have to go through as long. If you go into catalog, don't just scroll all the way down to R, because there's like hundreds of functions in there. Just press the R button and it'll jump you to the R's, and then you just have to scroll through a few of them. So let's take a break now, come back at 2:09, and I guess the first thing we'll do is, in groups, let's go through that problem that you wanted to do, and it'll give you practice using this approach to solving problems too. Okay.